Thanks very much, Anna, and welcome again. I'm Ben. I'm Platform Lead for Surface Characterization in the Faculty of Science and Engineering here, focusing on the HAXPES today. And just a big welcome to Manchester, noting it's a really exciting time for us. So we're marking our 200 years since our inception. And actually this week, possibly even today, I can't remember the actual date, marks 20 years since the first isolation of graphene. But full disclosure, there will be no graphene in this talk. Okay, hurrah. So we're really proud of our photo emission facilities here at Manchester. We like to think of ourselves as a centre of excellence. In one laboratory, you've got a real combination of laboratory-based techniques. So this includes near ambient pressure XPS, where we can look at the interaction of surfaces with gases. A lot of standard XPS. Again, as we've talked about, really important for quantification of the elements, chemical state analysis. That's complemented by valence band studies that we can do using ultraviolet photoelectron spectroscopy, just to kind of enhance the signal from the valence band. And obviously today we're focusing on our hard X-ray photoelectron spectroscopy system from Scienta Omicron, where we're looking from the surface to the subsurface, or bulk-like. We shouldn't really say bulk. And that's complemented by depth profiling that I think has been mentioned a few times as well. So we've got monoatomic etching and cluster etching sources. These are destructive and they will change your chemical state, but it does allow us to kind of depth profile over much deeper regions, such as hundreds of nanometers. And I'll come back to how we actually can complement that with HAXPES as well. Just noting, if I can get rid of this box. So our facilities are on some Manchester research websites, noting that we are part of the EPSRC National XPS Service, also known as Harwell XPS. So that's a route for access for UK academics. And also, as David pointed out this morning, in the Royce, there are also access schemes that's for academics in the UK and in Europe, as well as industrial customers, and access schemes particularly for small to medium enterprises. So, Alex, I'll admit them. Right, so we've got 5 instruments here. So we've got the Scienta Omicron system, which is the HAXPES, and that's coupled to a high throughput system, because you always need high throughput XPS. That's actually coupled under UHV, and there's a preparation chamber as well, vacuum suitcase, etc. Our near ambient pressure system is from Specs, and we've got one very old and one very young Kratos high throughput system, and Ultra and a Supra. I skipped. So I'm going to start with some more simple examples. We've had some more sophisticated analysis so far, so I'm kind of taking a step back. I'm kind of continuing from where Alex finished this morning. Some simple examples to highlight the real advantages of talked about. It's less sensitive to surface contamination. So it's an example of a very dirty, as received, unknown provenance zirconium sample, where in the XPS survey we see a huge amount of carbon. We can measure with XPS a bit of the lattice oxygen, but we're mainly seeing contamination in the oxygen spectrum. And the HAXPES allows us to probe the metallic through the passivated oxide layer. So it's a nice demonstration that we can access deeper core levels. So in the case of zirconium, we can access the zirconium 2s and 2p core levels, which you can see in the HAXPES survey has a real increase in sensitivity. And we're accessing the different Auger transitions that maybe just haven't been measured before. We can detect buried interfaces. So we've also already mentioned gallium nitride today, just because it's a nice example that it's difficult with aluminium KL for XPS to measure the nitrogen 1s peak, because it's disturbed by the gallium Augers. So we can detect in this case the indium in a thin InGaN layer buried in gallium nitride. The quantification has been established for this instrument with our colleagues at MPL for the notable paper by David Kant. We can quantify the atomic concentration of gallium, nitrogen, and indium, and then we can use a layered model to extract the expected stoichiometry within reasonable error. We can detect materials of interest under capping layers. So a lot of analysis, it's really important that they might have a top electrode, or they just want to seal their material. So on the left here, you've got an example of some manganese aluminium alloy that's underneath a tantalum capping layer. I think somewhere between 5 and 10 nanometers of tantalum. This is actually a really fast measurement. We've talked about accumulation times, but we actually measured maybe, I would say, dozens of these samples because they were tuning their deposition system. They wanted to get the aluminium to manganese ratio. We were able to check the quantification. We did some checks that our quantification was working, and then actually we were measuring one sample, just a couple of core levels every 10 minutes, and it was actually quite a fast high throughput measurement. Another nice example, this is from MPL as well, is looking at insulating materials. So we've talked about charging. Often at synchrotrons, you wouldn't be able to look at insulating materials because you can't charge neutralize, whereas in the lab, you can have a low energy electron gun that solves that problem for you. So here, these are some PTFE, PMMA core shell nanoparticles. We can detect the fluorine in the core. It's a bit noisy, but it's there. Through about 35 nanometers, and these are distinguished, these are very well characterized, that the core is actually offset, and again, some calculations from the quantification can be done to verify that. In terms of looking beneath things as well, we can look below damage layers. So we've talked about depth profiling, and a lot of other techniques that we use are destructive processes such as plasma etching, glow discharge etching, and the in-vacuum etching processes that we've mentioned. Those are well known to create a damage layer, so they can be particularly monoatomic etching sources can be highly reductive. So you're ripping out your smaller atoms more preferably. You're reducing your oxides to metal state very readily. We've shown that the damage layer induced by those processes looks to be typically the order of a few nanometers to 10 nanometers. So the HAXPES at this high energy again allows us to probe below that damage layer, and we can extract. Keep having to move this. You can extract the expected stoichiometry without having to do use the XPS and say how much oxide have I got, remove that from my quantification, etc. And again, more routine measurements in that way. And what's nice here as well is that again, we're using the deeper core levels of the phosphor 1s and the indium 2p are incredibly strong, a greater sensitivity than XPS. I'll come back to that in a few slides. So actually the measurements are very, very fast. We've talked about the inelastic background modeling a few times now. I think just for those that maybe need a little bit more of an introduction, this is a real classic example from Sven Tugard on the left-hand side of copper. So if you take the intensity of the copper peaks and calculate an atomic concentration, you get exactly the same amount of copper, okay? So if you just use the peaks, you say, okay, I've got X amount of copper in my sample. But as you can see, the backgrounds will change very, very distinctively depending on the morphology of the sample shown above. So actually, sometimes you really do need to look at the background to establish the morphology of your sample. And I think, as it's been mentioned, this is seminal work of Sven Tugard over many decades. Just want to highlight, I think, Paul mentioned that, for instance, the cross-section is very important. Establishing the inelastic mean-free path is very important. If you've got layered structures, those might be quite different, and then you need to look at hybrid cross-sections and inelastic mean-free paths. So then reference materials become really important, and it needs a high level of expertise, I would say, to kind of do that in a reproducible way. So some of the work that we initially did with MPL, because we really wanted to understand how deep can we measure, okay? What's the deepest that we can see non-destructively using this technique? So we used, as Alex has already mentioned, an iridium containing organic complex that sort of sat on an organic underlayer with different overlay thicknesses. So you can see on the left-hand side, we've got a reference material, which is the iridium sample. And again, we're looking at the deeper core levels here, so higher than you'd normally measure with normal XPS. And then we start to bury it over different overlay thicknesses, and the signal drops off, but you can see that the background remains. And then we can use the inelastic background modeling to model that. And you can see on the left-hand side, we sat at 1 photon energy and looked at different overlay thicknesses. And on the left-hand side, we used 1 overlay thickness, this is 25 nanometer overlay. And we've changed the photon energy here, so from 6 to 10 keV. So again, we're changing our sampling depth, so we're able to probe through more or less of that material. So it's kind of analogous there. So this was a benchmarking exercise to our lab system, which we've Alex has already shown this. Notably, again, here we're actually now using a 1 micron underlay here, so much more insulating sample. We couldn't measure this at IO9 because it charged up too much. And we won't talk about beam damage either. They kind of got a bit destroyed. Whereas the lab source, we don't believe damaged the sample, which is preferable. And again, we can look up to quite nice overlays of about 200 nanometers. And what we do in this paper is we kind of establish, let's say, an ideal or maximum sampling depth of information we can extract from, which we call the inelastic sampling depth, which is about 20 times the inelastic mean free path of electrons rather than 3 times the inelastic mean free path, the normal XPS definition. And just to note here that the iridium, the amount of iridium in this organic complex is about 3 atomic percent, so you can get an idea that it was very easy to measure. The sensitivity of the iridium, again, is actually boosted compared to XPS, and we were able to measure these over layer thicknesses within reasonable error. So I'll just come to a more realistic example, building on a lot of work that's been done at Manchester, in particular on organic hybrid perovskites. So this is lead iodide based, with other ions in it. So in this case, formamidinium. They are very promising for next generation solar materials, but they do have high vacancy concentrations. And the latter can decompose quite readily. They're very prone to thermal and moisture induced damage. So a lot of work has been done to modify these materials to improve their stability and improve their device performance. So in this case, some of the ions are replaced with cesium, and there was also an addition of rubidium. So we use HAXPES to kind of, again, get subsurface or bulk-like information. The important thing to note here is that actually with normal XPS, it was really, really difficult to detect the rubidium at all. Okay, so it's a relatively low concentration of rubidium. With the HAXPES, we actually get about an 18 times increase in sensitivity compared to what we'd be able to measure with XPS. There's no peak overlaps, so we're able to detect that and be much more confident that it is there and to also quantify it. What's quite like about this survey, apologize, it's a bit difficult to read on this screen, but we've kind of got sets of peaks at the high binding energy range. So for instance, lead, iodine, cesium, and the rubidium. And then there's the low binding energy range, which say that the low binding energy range you would normally measure with XPS. And because you're at very different binding energies now, you're at very different kinetic energies, so you're actually getting depth resolved information in this one spectrum now. So we can start to look at what's the stoichiometry of iodine using the deep core levels, which is a bit more surface sensitive, compared to the lower binding energy core levels, which is a bit more bulk sensitive. We can then do angle resolved XPS with the HAXPES to probe the stoichiometry. These materials are notorious that there's loss of iodine at the surface. We can establish the true stoichiometry of the material at the greatest sampling depth with HAXPES, and we can track towards the surface and see that actually the loss of iodine here is over about 30 nanometers. But interestingly, here you can see that the depth profile of the cesium and rubidium is actually much less dramatic than that. We've also looked at then some electrical measurements on these materials. So this isn't formamidinium lead iodide. This is more traditional methyl ammonium lead iodide. And we've done some electrical measurements. So directional bias. So the sample is in a mount. You've got your source electrode essentially at the top and the drain electrode at the bottom. We can move our measurement position to the top and the bottom. We can do our directional bias, noting that on the bottom, as these materials decompose, they will decompose to lead I2 and it turns bright yellow. So we were very careful in our experiments to make sure this didn't happen. This only happened the first time. But it just goes to show that we are really applying the electrical bias. So what you're looking at here, you've got source and drain, and you're seeing, hopefully you can easily, there's a lot of information here, you easily see that there's opposite behavior at the source and the drain. So we're tracking the iodine to lead ratio here. As a negative bias is applied, that drops. And then as it's turned off, it returns back. Okay, so we're seeing that as the polarity is switched, it switches the direction. It does return back to nominal at room temperature. So this is reversible ion migration that we're measuring. It actually corresponds to a significant change in the vacancy concentration, and we've actually then used that to extract the ion vacancy mobility and the diffusion coefficient. Okay, so to summarize, HAXPES offers sort of subsurface bulk-like information, less sensitivity to contamination. We can probe through passivation layers, capping layers, damage layers. The depth information over such a broad kinetic energy range is giving us depth information in one spectrum, but using the analyzer in an angle resolved mode, we can actually get one-shot depth profiles as well. We can actually get enhanced sensitivity for higher Z elements, as it's been seen now. You solve the issue of Auger peaks being in the way. You can look at core levels from different elements that are separated better. We can get a greater ultimate probing depth using inelastic background measurements, and in the lab, electrical heating measurements and measurements of insulators are just a lot more straightforward. So with that, I'll just thank everyone that's contributed to that, and thank you for listening.